Okay, so I'll try to make this quick. So problem 8, here's our system of differential equations. Here it is in a more nicely packaged form. We want the general solution, so we want to solve the eigenvalue problem for this matrix. Alright, I did it, or rather I had a computer do it, which is totally fine for you to do, and I got these eigenvalue-eigenvector pairs. You can see that it's definitely a very good situation because I'm getting two distinct real eigenvalues, but it's a very different situation from what I had last time, since the eigenvalues are both negative, as opposed to last time we had one negative, one positive. So that's going to give the critical point 0 a very different kind of character. Alright, let's write down the general solution. There it is, C1 times, and then one of my fundamental solutions plus C2 times another one. And as always, I'm building these solutions by doing e to the eigenvalue times t as a scalar times the vector, and then an eigenvector for the vector. So I'm just going to pick one to plot as green and one to plot as blue. And then let me plot the eigensolutions in the phase plane. So now let's think about, as in the future and towards the past, t goes to infinity or t goes to minus infinity, what are the tendencies for a general solution? And actually no, let me do this after. First, let me just plot the eigensolutions, so the green and the blue. So that way I get my plane separated into 4 regions. So this one, well, it's all scalar multiples of -3, 1. So -3, 1, something like this. And wherever I'm starting, as time goes towards the future, this just decays, right? So the coefficient in front decays. I'm looking at straight line solutions heading towards the origin. So these are the types of eigensolutions I get. As t goes to infinity, these approach the origin. Now, in red here, these questions are about general solution, not just about eigensolutions. So let's save this for later. How about the blue eigensolution? As time goes to infinity, they also go to 0, but this time they're traveling along the direction -2, 1. So -2, 1. That's like just a little bit shallower than -3, 1. Now I wish I had exaggerated this a little bit. Sorry, what am I saying? -2, 1 should be a little bit steeper, right? So, I don't know. Let me exaggerate the drawing anyway. So let's pretend that -2, 1 is like very steep, like this. It's not really that steep. And towards the future, you go towards the origin. It's because of this e to the -t. This decays as t goes to infinity. And towards the past, you're coming in from far away, right? So if I send t to -infinity, then this term blows up. So as t goes to infinity, the position actually approaches the origin, right? And as t, because both terms are approaching the origin. So in any general solution, if I do the entire thing kind of in red, for any general solution, we approach 0, 0. So the origin is actually stable here. This is what it means to say the origin is stable. So 0, 0 is stable. But that's not enough to answer the question here about the kind of critical point that it is, because there's more than one kind of stable critical point. So is it a stable node? Is it a stable spiral? Or one of the other stable things, maybe? So just to fill in the picture, let's answer one of the harder questions here. Oh, let me fill in this easy question. As t goes to -infinity, let's answer the hard question. So as t goes to infinity, as I look towards the future, what is the direction approach? So this time, it's not like one term is, both terms are actually dying off, right? As t goes to infinity, both of these two terms die off. But one of them dies faster. So which term, the green term or the blue term, dies faster? And then which term is left over? If you look, this is decaying with a faster rate, a decay rate of 3. That's going to make it die a lot faster than this one, right? one way to think about it is that the decay rate sort of acts multiplicatively on the whole thing. So like if you have e to the negative 3t, then that's e to the negative t times e to the negative 2t. So this term is like this term, but with a whole e to the negative 2t, a whole other exponential decay term multiplied by it. So this will decay very fast compared to this. So the green is just going to totally be negligible as t gets, I mean, they both become negligible as t gets smaller and smaller, but the direction is going to be much more parallel with the blue. So the direction approaches the direction of negative 2, 1. So as solutions approach so solutions will always approach the origin towards the future, but they approach sort of, their direction of approach is parallel to the blue. So like this. This is the direction of approach. You see, if you zoom in here, it's parallel to the blue. And like this. Like this. Parallel to blue. And as you look towards the past, you get the opposite behavior. The signs sort of flip around things because of the minus signs. So the direction, if you start putting in negative 1,000,000 for t, then you'll see the opposite. This actually dominates the direction, and this is going to be negligible in comparison. So the direction approaches that of negative 3, 1. So you're going to come in parallel to the green line. So like this solution, I expect it to come in from up here, parallel to the green line, so something like this. And then approach 0, parallel to the blue line. This one, come in parallel to the green line, and approach 0 parallel to the blue line. This one is going to come in parallel to the green line, so I have to do a whole curve like that to draw that. This one will come in, it's going to come in parallel to the blue line. Sorry. Towards the future, it goes to the origin, and it approaches, and its direction of approach is parallel to the blue line, but it's coming in from the past, from being more parallel to the green line. So you get solutions that look like this. So this is stable. This picture is the picture of a node. This is called a stable node. So the origin here is a stable node. So now you've learned about two critical points, saddle points and stable nodes. Saddle points you can detect by the eigenvalues being opposite signs, like in the previous videos we had 2 and negative 1 for our eigenvalues. Stable nodes you can detect by seeing the eigenvalues both being negative. And can you guess what an unstable node is? That's where the eigenvalues are both positive. You get basically the same picture as this actually, but with the arrows all flipped around, and it would be unstable. Okay, and I just stuck this general solution here into the same code from before just to make this plot of this node. Here the origin would be called a node. And this node is kind of exaggerated because these two eigensolutions are so close together. My picture actually exaggerates how far apart they are. Really, the blue is quite close to the red. The blue is quite close to the green. They're not very different slopes. So here you can see just how skewed the picture is. In this situation, it almost looks like solutions are trying to spiral towards the origin, but they don't quite ever spiral. Instead, they just do this sort of curve, and then they come in and decay towards the origin. Now you can get spirals, as suggested by the fact that these are options here, these spiral options, but those are not going to be answers on these problems. They'll be answers on later problems. Spirals are what you get when you have complex eigenvalues for your matrix of coefficients.